Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 9. Roots of a Polynomial. Polynomial Reduction and Synthetic Division. Any root-finding method can be used to find a real root of a polynomial. Finding a single root of a polynomial with a suitable method is simple, but determining the remaining roots with a different starting guess can be problematic because the method may produce a root that has already been found. Once a root is found, it must be eliminated to avoid the possibility of getting the same root. Polynomial reduction, or polynomial deflation, is a technique to remove a root, say, x equals alpha, from the original polynomial. To achieve this, the polynomial p sub nx is divided by x minus alpha, which leads to the quotient polynomial q sub n minus 1x of degree n minus 1. This new quotient polynomial no longer has x equals alpha as its root unless x equals alpha is the multiple roots of p sub nx. Consider the following nth degree polynomial. Dividing p sub nx by x minus alpha results in, where q sub n minus 1x is the quotient and r0 is the remainder. 4x equals alpha, as being the root of p sub nx yields r0 equals 0, i.e., without a remainder. Expanding p sub nx in the right-hand side and grouping like terms gives the following. By matching both sides of the polynomials, the following sequence of constants is obtained. Reducing the quotient q sub n 1x by x minus alpha results in the following polynomial of n minus 2 th degree, where s sub n minus 2 is a quotient polynomial of degree n minus 2 and r1 is the remainder. Combining p sub nx and q sub n minus 1x yields. Its derivative becomes, adopting the Newton-Raphson method to find a root of p sub nx, we need to evaluate. Then, the Newton-Raphson iteration equation can be expressed as follows, where p denotes the iteration steps. The iterative procedure is terminated when the absolute difference between the current and prior estimates is less than a tolerance value. To be cautious, note that when a polynomial is ill-conditioned, polynomial reduction can lead to a degradation of accuracy in the coefficients of the reduced polynomial and, subsequently, in estimated roots. To reduce the effects of such errors, consider using the approximate root as the initial guess to find another root of the original polynomial. The advantages of the method are: evaluating polynomials using synthetic division is computationally cheaper and easier since it does not require powers of x. There is no risk of getting the same root, except for a root of multiplicity m greater than and equal to 2, since the root is factored out once it is found. The algorithm produces the coefficients of the reduced polynomial, q sub n minus 1x, as well as the remainder, r0, which provides information on whether the root is found or not, i.e., r0 equals 0. The disadvantages of the method are: a random, unintelligent first guess could result in a large number of iterations. Every root is obtained with finite accuracy, and the numerical errors in the coefficients of the reduced polynomials could build up so that the computed roots thereafter could become even more inaccurate. The order in which the roots are found can also affect the coefficients of reduced polynomials. The method may suffer from instabilities when the roots are sensitive to small changes in the coefficients of the polynomials. Polynomials with roots of multiplicity are also sensitive to small changes in their coefficients. Find the real root of the following fourth-degree polynomial using the method of polynomial reduction. The initial guess is given as x0 equals 0. For the convergence criterion, use absolute difference between the current and prior values with 10 to the minus 5 as epsilon. We will start by identifying the coefficients of the polynomial as array A. We take the coefficient of x to the fourth as a4 and assign the following coefficients as a3, a2, a1, and a0. We will tabulate all the results obtained in each iteration. The initial guess is placed on the left of the table. The recurrence relationship to calculate b's is given by as follows. We set b4 to 0. 4k equals 3. This relationship takes the following form. We substitute the numerical values for a4, b4, and alpha 0. We get b3 equals 1. Next, 4k equals 2. This recurrence relationship takes the following form. Substituting the numerical values for a3, b3, and alpha 0. We find b2 as minus 1.3. 4k equals 1. We obtain the following expression. Substituting the numerical values for a2, b2, and alpha 0. b1 is found as minus 13.4. And finally, for k equals 0, the relationship leads to the following expression. We substitute the numerical values for a1, b1, and alpha 0. We obtain b0 as 28.5. Now that we have b's, we can go on to calculate c's. We set c3 to 0. We begin with k equals 2. The recurrence relationship takes the following form. We substitute the numerical values for b3, c3, and alpha 0. c2 is found as 1. 4k equals 1. The recurrence relation becomes substituting the numerical values for b2, c2, and alpha 0. c1 is found as minus 1.3. 4k equals 0. We have the following relation. Substituting the numerical values for b1, c1, and alpha 0. c0 is found as minus 13.4. The remainder term, R0, requires A0, B0, and alpha 0. We find R0 to be minus 10.8. Similarly, the remainder term, R1, requires B0, C0, and alpha 0, which also yields 28.5. The current estimate for alpha is obtained using the Newton-Raphson method as follows, which yields 0.378947. We will be skipping the detailed calculation of B's and C's. B's are calculated using the A's, and C's are calculated using B's. The second estimate is obtained as 0.488624. The third estimate is found as 0.49988. Here we may also watch our 0 for convergence since it is the remainder. The fourth estimate is found as 0.499999, and the absolute error is 1.2 times 10 to the minus 4, which does not satisfy the convergence criterion yet. So we will iterate this one more time. The fifth iteration yields 0.5, and our 0 is less than 2 times 10 to the minus 7, which satisfies the convergence criterion. The array B is the coefficient of the quotient Q3. That is all for now. See you next time with another topic. Bye.